When an unprotected backend server receives thousands of requests in a matter of seconds, the hardware begins to choke. The system starves for resources, the processors peg at maximum capacity, and the entire application drops offline. Denial of service attacks saturate server capacity, forcing processors to lock up and initiating massive cascading failures across the infrastructure. If your backend calls paid third-party services, like Stripe for payments or an LLM for data processing, a sudden flood of excess traffic generates thousands of dollars in cost overruns in a matter of minutes. The standard defense mechanism to protect these resources is a rate limiter. It enforces strict programmatic fair usage, capping exactly how many requests a single client can send within a specific time window. Without one, your API is effectively an all-you-can-eat buffet, left entirely open for bots, bugs, and malicious actors to consume at will. Building an effective rate limiter requires strict engineering discipline. The system must accurately track millions of users simultaneously, operate efficiently across distributed environments, use minimal memory, and introduce near-zero latency. The first decision is where to actually put the logic. Client-side implementation is an immediate non-starter. You can never trust the client. Front-end code is easily bypassed or forged by a malicious actor. Embedding the rate-limiting logic directly inside your core application code is also problematic. It creates a tightly coupled, messy architecture that is difficult to update across multiple backend server fleets. The optimal placement is extracting it into an API gateway. This diagram shows the rate limiter acting as a dedicated, centralized bouncer, sitting right in the middle between the external client devices and the internal API servers. The primary job of this gateway is rapid interception. As illustrated here, when a client exceeds their allowed threshold, the gateway immediately drops the request and returns an HTTP 429 too many requests status code back to the client. By isolating the rate-limiting logic into this separate middleware layer, BAT traffic is killed before it can ever touch your core application. This allows your backend servers to remain completely stateless, focusing entirely on executing their primary functions. To decide which requests get dropped, the API gateway relies on mathematical rule sets. The most widely adopted is the token bucket algorithm. It defines a conceptual container using two strict metrics, a maximum capacity and a preset refill rate. This diagram shows the mechanics in motion. A background process steadily drops tokens into the bucket at a defined interval. Once the bucket hits its maximum capacity, any newly generated tokens simply overflow and are permanently discarded. The core rule is absolute. Every incoming request must consume one token. This flowchart tracks the logic. If enough tokens exist, the system extracts one and forwards the request. Following the bottom pathway, if the bucket is empty, the request is instantly dropped. An alternative approach is the leaky bucket algorithm. As shown in this diagram, it utilizes a first-in, first-out queue. Instead of consuming tokens, the requests enter the bucket and are pulled out to be processed at a strict, perfectly fixed rate. The behavioral difference between the two is significant. Token buckets allow for sudden, localized bursts of traffic. As long as the user has tokens saved up, they can spend them all at once. Leaky buckets iron out those bursts, enforcing a perfectly stable outflow. But the leaky bucket contains a critical flaw. A sudden burst of traffic will rapidly fill the queue with old requests. Because the system can only process them at a fixed, rigid speed, new valid requests arriving seconds later will be starved out and dropped while waiting for the bottleneck to clear. Both of these bucket algorithms shape traffic efficiently. Their success in production, however, relies entirely on the engineer tuning the capacity and refill parameters to exactly match real-world user behavior. The fixed window counter maps a timeline into rigid blocks of 1 second. Incoming requests increment a counter. Once the limit is reached, the system locks. Look at the gray blocks. Subsequent requests are dropped entirely until a new time block begins. The primary advantage of the fixed window is its extreme memory efficiency. The server only needs to hold a single integer in memory for each time block. But its rigid design exposes the system to a severe vulnerability known as the boundary burst problem. Imagine an API allowing 10 requests per minute. A malicious actor could fire 10 requests at 1:59 and another 10 at exactly 2:01. Because the time window reset at the top of the minute, they successfully pushed 20 requests through the gateway in a 2-second burst, artificially doubling their allowed limit. While fixed window counters require almost no memory to run, their inflexibility leaves the system highly vulnerable to timed adversarial traffic spikes. The theoretical mathematical fix to the boundary burst problem is the sliding window log algorithm. Instead of relying on rigid, predefined blocks of time, this system logs the exact timestamp of every single incoming request. By evaluating the precise time differences between those logs, it constructs a perfectly accurate, continuously rolling time window for every user. The operational reality is that keeping a massive, continuously updating log of millions of individual timestamps consumes an unacceptable amount of memory. At enterprise scale, it is completely unviable. Look at this timeline. The sliding window counter uses a rolling time window, the dotted box, overlapping two fixed periods. If you are 30% through the current minute, it adds current requests to 70% of the previous window's total. This weighted average flattens boundary bursts. This mathematical smoothing makes the sliding window counter a standard choice for high-volume APIs. It provides the accuracy needed to prevent boundary attacks without the massive memory overhead required to log individual timestamps. Beyond the choice of algorithm, the system requires a data infrastructure capable of tracking millions of mathematical states simultaneously. Reading and writing these counters to a traditional disk-based database introduces too much latency for a per-request check. The solution is an in-memory cache, most commonly Redis. By keeping the data entirely in RAM, Redis executes read and write operations with sub-millisecond latency. The operational loop looks like this. The moment a request hits the API gateway, it triggers a Redis INCR command. This instantly bumps the numerical counter associated with that specific user's database key. To manage the cache, the system utilizes a self-cleaning mechanism. A Redis expire command attaches a strict countdown timer to the key. Once the limit period has passed, the cache will automatically wipe the counter, cleanly resetting the time window without requiring a manual database cleanup. True architectural speed is achieved by pushing the counting logic entirely into volatile memory, completely bypassing slow storage drives. In production, rate limits are rarely a single global number. The API gateway maintains granular VIP lists, applying entirely different algorithms and strictness levels. Based on specific IP addresses, individual user IDs, or particularly heavy database endpoints. The fully realized system relies on an API gateway positioned at the absolute edge of the network, executing a precise sliding window counter and writing state to a low-latency Redis cache. But deploying this infrastructure introduces new complexities. When you spin up dozens of these API gateways simultaneously across the globe to handle massive traffic, you immediately introduce race conditions and severe synchronization delays across the network. Rate limiting is ultimately a strict exercise in distributed state management. Success demands choosing the exact mathematical algorithm and the right storage architecture to ensure your layer of protection never becomes the bottleneck itself.